So I was asked to address one key question, and that's the question there. Is a new pandemic inevitable? And the answer is quite a simple one, and that's yes. But don't go yet, there's a bit more to follow. So we will, I'll try and I'll explain to you why I think we will get more disease epidemics in the future. So the answer is yes, but I also think there are reasons to be optimistic about how we can control and approach these infections. So what I'm going to do now is try and give you my evidence for why I think we will get new things and why we should be pretty upbeat about our way of covering them. So, of course, this talk is very well timed because we're in the midst of a very serious Ebola outbreak in West Africa, which is capturing headlines. Those interested in getting an update on the epidemic and the public health implications, I should direct you to the US CDC website. The US CDC website here is a really great one-stop shop for information about the Ebola pandemic, very well up to date and very nicely laid out. So this is a screenshot from that website. What you might also have seen are maps like this and numbers like this. So this is obviously a map of central West Africa. Ebola was first described here in what was then the border of Zaire and Sudan. It's now the border of Congo and South Sudan in 1976. And from 1976 onwards, there have been Ebola outbreaks across this region of central West Africa. Some people argue that the virus has moved like a wave across the region. Whether that's true or not, I'm not exactly convinced, but we know they've occurred here since the mid-1970s. And of course now we have an epicentre in the far west of the continent, centred around Guinea, Sierra Leone and Liberia, their kind of border region there, but also some sporadic outbreaks in Nigeria and Senegal. So today's numbers, which I'm sure you've heard them, are very well documented in the press now, today's numbers are about 5,000 or so cases and about 2,500 deaths. The mortality rate is about 49%. Now interestingly, exactly concurrently with that outbreak, the second outbreak going on right now in the Congo. So there, this is actually a slightly different strain of virus. We don't know much about it, but it's also happening simultaneously with the main outbreak of Ebola in the west of the continent there. So there's been a lot of discussion about this, and so I should say now, why is this outbreak so much worse than any of those? It really is by order of magnitude. And I think what's happened for the first time is that Ebola has normally emerged in these very remote rural parts of central West Africa. And it's burned itself out, and we treat it very, very quickly. Here, for the first time, infected individuals have moved from where the zone of emergence, about here, the border region through countries, into cities and towns, and they brought the virus with them. So it's the movement of infected people into big urban areas that see the epidemic for the first time. That's why it's got going. And there is clearly an unfolding humanitarian crisis in this region that we really need to act on very, very quickly. So that you may know about. I've also just plotted here, actually not I have taken this from a paper, just plotted the number of cases, you can see that's the red, against the number of deaths in this outbreak through time here, okay? And you can see two very interesting things. So one, the rate of increase in cases is increasing, the epidemic's accelerating, okay? So whatever's going to happen, this is a long haul. We're clearly get a lot more cases. We're a long way from the peak of this yet. We'll get a lot more cases and a lot more pain to go. How many we're going to get is a very difficult thing to estimate, but I don't think now we can rule out hundreds of thousands of people to be infected, so it's a big number. Second, the death line is here, that's in black. And you can see that by eye, it looks like the mortality numbers is decreasing relative to the cases. So it looks like there's less deaths now than there was at the start of the epidemic. Now, I've heard arguments that may be due to the virus becoming less virulent. I'm not convinced that's the case. I suspect what's going on is that we're just better at dealing with Ebola now than we were a few months ago. And there's more medics involved in the control. And I also suggest to you that if Ebola, so this is obviously a very impoverished part of the world with very poor medical infrastructure, if Ebola was to emerge in a Western country, I would suspect the death rate would be lower than this as well. I think this is partly a function of where the virus is occurring. What's also very important about Ebola, that's central to my talk here, is we think we know where it came from, and that the reservoir species, and we'll hear about reservoir species shortly, are bats. So bats, so the reason why it's in this part of the world here, is the bats at the reservoir, they live here. And bats carry lots and lots of viruses, including Ebola. And so what we think happened is that these bats, this bat virus here, this is again from CDC, these bat viruses jumped either directly to humans or to an intermediate species who then passed to humans. And those intermediate species could be chimps and gorillas. And interestingly, chimps and gorillas are also dying off from Ebola. So Ebola is a big threat to the great apes in this one too. So the chimps and gorillas get to humans or dicots, deer-like animals that could pass on. So you think that's the cycle. So what Ebola is, and we'll hear more of this later on, is that it's a virus that's jumped from an animal to a human. I call that cross-species transmission. And I'm going to show you that many diseases we have in humans, infectious diseases, are caused by that process of viruses jumping from an animal into a human. That's called zoonosis. So that's Ebola. That's today's obviously major concern. If we wind the clock back 11 years, the major concern would have been SARS, which had a similar kind of media impact at the time. So I'm sure you're familiar with SARS. Just to recap what happened, it emerged late 2002, early 2003 in China, spread to a few cities, particularly Hong Kong and Singapore. It burnt itself out in about July 2003. After it had done that, the total number of infected cases about 8,500. Of those, about 10% died, 800 deaths. Okay. The total cost of SARS was about $40 billion. That really kind of, again, focused people on these new emerging diseases. So that was SARS. That was obviously very, very big media news. Interestingly, at exactly the same time as SARS was a second outbreak of disease, which was completely under the radar, but to me was almost more worrying. And that happened in the Netherlands. And it was an outbreak of avian flu called the H7N7 strain. I'll discuss all these strains shortly, but this avian flu, bird flu strain emerged between February and May 2003, exactly the same time as SARS in the Netherlands. And the Dutch authorities clamped down very quickly on this outbreak of avian flu. And their culling and the virus led to the death of 30 million chickens. A third of the Dutch poultry industry is wiped out very, very quickly. So this is the doomed chicken, I apologise. And that may have cost about $1 billion in disease control and industry losses. And there are in fact there are 89 human cases of that virus. Now this is very interesting. So these human cases, each one is a separate jump from a bird, a chicken, to a human. There's no human-human transmission. Each one is what I call a spillover. So the virus jumps from a human, infects that human, and then dies out. Okay, so that's the kind of first stage of emergence. Discuss the virus later. So 89 chicken to human jumps, and one person died, and that person was actually involved in control of the virus. And I said that to me this is actually in some respects more worrying, but I argue also that although Ebola is a horrendous thing and a major humanitarian problem in West Africa, frankly, personally, I'm still more concerned about avian flu on a global scale. So SARS, Ebola, H1N1, influenza, these are all examples of what are called emerging infectious diseases. That's those that are new or increasing in frequency. And you can go to the web, you can find lots of discussion and pictures and papers about these. Here you find maps like this, just showing where diseases, new diseases or things that have changed, increasing frequency, have appeared in recent years. Okay, I won't go through them, so you yourself are kind of familiar. In the Australian region, we have Hendra, obviously in Queensland, and nearby we have EB71, quite a nasty neurotropic disease, and Nipah, which is like Hendra. So there's lots of things emerging. Now, as I've said, with Ebola, with SARS-CoV-2 as well, I should say, and from avian flu, in each case, what's happened is that the virus, and it may not be a virus, it can be a bacteria, it can be a fungus, they jump from an animal to a human, so they cross the species boundary. And this little map here is like a heat map. It's just the darker the colour is showing you where more of these jumps from animals to human are taking place. You can see very clearly that Asia's, Southeast Asia, South Asia there, is the real kind of hot spot for where this species jumping is taking place. And of course, the worry for a country like Australia is we are no longer isolated by distance, because, sorry, this is the light's slightly dark now. The global travel network is so intense now that we have one connected world. So what you really can't see here is a map of the world, and the lines is global flight traffic. This is a very famous picture from the 2009 swine epidemic. This is USA here, lots of flight traffic. What you can't see is that Australia is really connected now to this part of the world by direct flights. So a virus that jumps species boundaries in Southeast Asia, for example, could quite easily get to here just because the flight traffic is so intense. So that's emergent diseases. Now I'm going to talk about human disease today because this is an earlier presentation. But I should say exactly the analogous process occurs for many other species too. For example, plants. So plant diseases are a major economic cost to agricultural industries, and there are many emerging plant diseases. So here's one example. This is some very nice work by Robert Parker in Sydney. These are stem rusts, so fungi that infect cereal crops. A little table there just showing you over the last 200 years, there have been a variety of these very nasty global stem rust outbreaks that have cost lots of money. In Australia, like viruses, but in humans, there are an increasing frequency of exotic stem rusts coming in that could, they haven't yet, they could ignite an epidemic of stem rust in Australia. So you can see increasing numbers through time. So this is actually quite a problem. There's also a new kid in the block, that's called myrtle rust. So myrtle rust is another fungus, came from South America about 2010. It's spread right across the east coast of Australia. This map's like over Victoria up to Queensland. So lots and lots of activity. And the worrying thing is, this fungus could really cut a sway through indigenous forests and native forests. So it's actually a very worrying situation. So plants and humans, all things, can experience these emergent diseases. So my work here, my work as a scientist, what I do for a living, is trying to understand how emergence takes place. How do pathogens, particularly viruses, jump species boundaries and get going in new hosts? Okay. So again, my first bullet point there is I'm interested. Disease emergence is really about jumping the species boundary. And the word for that, a word you'll hear shortly again, is zoonosis. That's a thing that a virus or a bug that can infect humans and animals. So how does that take place? And a simple way you can do that, it's a bit simplistic but it kind of helps, is to think about there being 3 stages or phases of emergence. So 3 types of interaction between these viruses and animals and humans. So the first is what I call a spillover or a dead end, like that 87N7 outbreak. And so what happens here is the virus, or whatever it is, jumps into a human, it infects that one individual, and there's no onward transmission. It can't get going, it's not quite established. So it's a dead-end infection. And avian influenza, I'll stress more shortly, particularly H7N9, are typical spillover, dead-end infections and don't get going. Stage 2, or phase 2 if you like, are those that we have a limited outbreak. So the virus jumps and it spreads a while. There is some human-to-human transmission, but it burns itself out. It can't establish, it can't cause a global pandemic. Now traditionally I put Ebola in that kind of second class, because traditionally Ebola infected a few people, maybe tens, a few hundreds, and then burnt itself out. Now I'm not so sure, maybe Ebola's gone beyond that now. And the third phase are those that become endemic human pathogens. They've adapted totally to the human cycle of transmission, and they're endemic in our species, the sustained human transmission. And there are many of those like HIV. So the key question I address is how do pathogens, viruses, move between those stages? What dictates that? Suffice to say, there's lots of things involved. There's genetics, there's immunology, there's also ecology and evolution, so kind of stuff I do a lot of. So I'll just give you one bit of technical detail, actually, that's really quite useful, I think. It's a number you hear a lot about in the media and in movies, and that's called R0 or R0. This is the basic reproductive number. So it's a really simple bit of disease ecology that's very important to learn. And all it is the number of, I've written it there for you, it's the number of cases caused by a typical infected individual in a susceptible population. So it's how many people, on average, you infect in an epidemic. So if I have a cold, if I cough here, I can infect Bruce and this person here, and you infect 2 other people. R0's 2, it's infecting 2 people. Okay? So obviously, for a disease to keep itself going, R0 has to be at least 1. Each virus has to infect 1 other person to keep the chain transmission going. What disease control is aimed at, so vaccines and drugs or just intervention, is to try and get R0 less than 1, because then that's then going to burn the thing out. So we try to intervene by pushing R0 less than 1. Of course, R0 greater than 1 means the virus has got going, it's causing an outbreak, an epidemic. And the bigger the R0 is, on average, the worse things are going to be. Just give you some numbers to kind of help you kind of focus this. So, seasonal flu, I had the vaccine this year, I got flu, the vaccine's not very good this year. Seasonal flu, the R0's about 1.5, so not very high, okay? HIV and SARS, about 3, okay, so a bit higher, so average 3 people infected by HIV infected person. Measles, a whopping 50, okay, so that was clearly vaccination was critical, high vaccination coverage, critical to dampen measles down. That's the first thing to kind of keep in your head. You'll hear more about that as time goes on. The other thing is to understand kind of fault lines. I think about disease emergence as almost like an earthquake prediction. We're trying to find the fault lines that allow species jumping to take place. So if you imagine these fault lines lie, if you imagine the kind of natural world here, so it's not very clear, but this is kind of the environment how humans and animals interact. You have wildlife, livestock, domestic animals, pets, animals that encroach on human populations, so sort of urban invaders, humans encroaching on animals. And all these interactions are linked up. And pathogens, see the fault lines. So pathogens can move between humans and animals at any one of those kind of intersects. So the arrows, the zones of interaction, a critical place to really understand how emergence takes place. So one thing that I'm involved in doing is just sampling microbes, viruses particularly, at those interactions, those fault lines, to see what's there. It's a whole different talk, but to cut a long story short, if you do that sampling at these kind of interaction zones, you find a myriad of viruses, a bucket of viruses. Animals carry an enormous number of potential human pathogens. Very few will ever emerge, but they carry a lot. Okay? So, given that kind of framework, we can start to understand a little bit about how disease, how human history and human ecology has changed, and what that's meant for disease emergence. So here I've classified as a whole of human history to 4 bullet points. Okay. So, apologies, I'm apologists. So, 50,000 years ago, 10,000 years ago, we invented farming. Okay, and farming was a really bad idea, I should say. Really bad idea. I should go back. A really bad idea in terms of infectious disease, because for the first time it allowed us to have big populations that were sedentary, and we live right next to animals. And of course, that made a new fault line for pathogens to jump species boundaries. So you can date the origin of lots of human disease, infectious diseases, for the origin of farming. 5,000 years ago, we invented basically urbanization, living in cities. And again, as becomes kind of obvious, that meant there were more of us, and that also allowed more pathogens to sustain themselves. We had many more infectious diseases. Classic work would be on measles, so it's really textbook stuff. So they showed that measles requires a population of about 250,000 to sustain itself. So that's the population size that the virus needs for R0 to get above 1. So if you go to the population islands that have less than 200,000 people, you don't have measles endemically. If you go to islands above 250,000 people, they can carry measles continually. So the more people we have, the more chance that happening. 3 years ago, of course, we had global travel, and that allowed us to go to exotic places and get infected by new things, and probably more importantly, bring our stuff to other places and infect people there. And sadly, the history of European colonisation has been the history of Europeans inadvertently bringing their pathogens to other countries that infected mining populations and wiped them out. So that's a very clear thing. And finally, the modern world, I'm going to say it's 50 years ago, so post-World War II. Lots of things there really accelerate the rate of emergence. So changing land use, like deforestation, what have you, highly connected networks, global travel, large populations, widespread immune deficiency. So there are lots of people now, particularly in sub-Saharan Africa, who are HIV positive, so weakened immune systems, and that potentially, it's not really shown, potentially could allow accelerate the process of emergence. The way we live today, just it's going to exasperate, it's a really big thought line, it's going to exasperate emergence taking place. Okay, so that's the kind of background. Now we'll give you the next part, just a few examples of past and present emergent disease, past and present zoonoses. Before I do that, I need to give you one quick technical lesson, very, very quickly. And that's, we're going to see a few of these weird liney pictures, very hard to see. these pictures here, this is called an evolutionary tree or a phylogeny. Okay? This is some screen grabs from the movie Contagion. Not a bad film about the disease, I should say, a bit hype, but not too bad. And so in that picture, they actually drew a tree, an evolutionary tree of this fake virus they invented as it was spreading through the human population. You're going to see a few of these, so just to make sure you know what they are. I apologise, this is very simple, but in case you don't know, an evolutionary tree like that, phylogeny, is exactly the same conceptually as a family tree that I'm sure you're all very familiar with. Okay, so this one I grabbed from the web here. So this is a family tree, so for example here, Hannah and Rachel, obviously more closely related to each other than either is to Bill and Sue. Okay, but they all share common ancestors with George and Mary. So that kind of family tree is exactly the same as the kind of evolutionary tree you're going to see shortly. But the evolutionary tree is kind of stretched in time. There's more events going on. Also, you'll see them in different orientations, but it's conceptually, just think of a kind of family tree pedigree. Okay, so the first example to talk about of emergent disease is the one I think really kicked the whole science off, and that was HIV/AIDS that we first described in the early 1980s. So every year, the UN AIDS Organisation published a document which is an update on the AIDS epidemic, and these are the last numbers they reported at the end of 2012. And the numbers are grim, but in fact they're better than they were. They get better every year. So at the moment there are 35.3 estimated, million people estimated with HIV in 2012. 2/3 of those live in sub-Saharan Africa. This is heat maps giving you prevalence. Okay, so darker kind of more HIV. So this part of the world here, huge HIV prevalence. It's had a major socio-economic effect on the population, as you might imagine. In 2012, there were 2.3 million newly infected people and over 1.5 million AIDS deaths. Okay, and amazingly, that again, this is getting better. Okay, that translates about 6,000 new infections each day. To put it in perspective, there's probably more infections today of HIV than Ebola in the whole of Africa since February 2014. So this is really still a huge public health problem. So that's the epidemic. Now, the great thing, well, there are some good news stories about HIV, and one of them is we've worked out its origins pretty precisely. So I'll just quickly talk you through it. It is quite instructive. So here's our first evolutionary tree, and I apologise for a bit of detail. What you're seeing here, these branches with names on, these are strains of viruses found in primates in Africa, non-human primates. So they're found in monkeys and they're found in great apes. Okay, so what that means is African primates carry a myriad of these viruses like HIV, called SIV, similar immunodeficiency viruses, and lots of animals carry them, lots of primates carry them in Africa. The key thing is, what HIV is the jumping of those viruses from these other primates into humans. So briefly, HIV comes in two flavours, 1 and 2. HIV2 is the least common one, it's really only found in people in West Africa. And HIV2 is a human symbol. Its closest relative is a virus with a thing called sooty mangabe. This is a very common monkey in Central West Africa. And the fact that human viruses are close to the mangabe one suggests that the virus jumped from mangabes to human. And we'll discuss how that might happen shortly. Okay? That's HIV2. More interesting is HIV1, and that's down here. And these three people, there's three people I should say, because there's been multiple jumps of this virus from its ancestor into humans. And the ancestor we think, you can read the tree there, the ancestor we think is chimpanzees. So chimpanzees very commonly carry a virus like HIV that's called SIV-CPZ, it's chimpanzee virus. And that's jumped at least 3 times, maybe 4 times into humans to cause the HIV-1 strain of AIDS, the AIDS virus. This is the culprit, it's common chimpanzee or pan troglodytes. And interestingly, there are 4 different subspecies of pan troglodytes. Again, this maps exactly the same area as where Ebola is, which is why the chimps are dying of Ebola. Okay, it's that same geographic region. There are 4 subspecies of chimpanzee, of common chimpanzee. 2 of them, I won't go the name, but the green one and the kind of, I'm colourblind, that purple, green and purple one. Those 2 species don't carry any viruses like this at all. but the blue one and the red one do, and it's the red one here, the chimps that live in this region here, they're the ones who have given us each time their viruses. And that's the subspecies Pan-Troidoides, and it's from Gabon, Cameroon, bit of the Congo. That's the kind of epicentre of the HIV. That's where the primates and the chimpanzees live. Okay, so that's the kind of, that's happened. The next question is, how did it happen? And there's no way we can absolutely ever totally resolve what happened, but I think we can come to a pretty plausible hypothesis. And again, hopefully it's not very clear, but so what I think happened here, again, it's to do the way we live in the modern world, is in the 20th century, the logging industry really expanded in West Africa, those parts of the map I will show you. So people went into the forest to cut down woods more and more and more, to encroach on the forest. And as they encroached on the forest for logging, they encountered lots of novel animal species, and that ignited a trade in what's called bushmeat, so just eating these unusual animals as food sources in Africa. So you can go to, this is a picture of a street market in Cameroon. There's a whole bunch of unusual mammals there for sale that you can buy for food, including primates. This is I think that's a cold, I'm not sure. And if you test those, you can find HIV-like virus in them. Okay, so this bushmeat trade is very, very likely to be the source of HIV. This here is very clear. This is a poacher was arrested. He had a sack on his back. In that sack was a baby chimpanzee living, the body parts were living inside. So I think the most likely scenario here is that you can imagine that when someone is butchering a chimpanzee or monkey, they're butchering to cut themselves, they expose the blood that's in that animal, and that's how the virus jumps into humans. I suspect that's, again, we can't ever resolve it, but I think that's the most likely source. So that's HIV. It's actually there's still a huge humanitarian problem some time after, although it's getting better. Now I want to wind the clock back and talk about an older, but probably in many ways even more deadly pathogen. And one that's actually around today, I should say. So you may have heard some news stories recently, this year in fact, of an individual living in a city in China who came down with the plague. And what the Chinese authorities, this person was affected by the plague bacterium from a rodent, and I'll discuss rodents in 1 second. This person was affected by a plague, and the Chinese authorities quarantined off the Chinese city to try and stop the plague spreading further. And what they were concerned about is this bacterium here called Yersinia pestis. It's an antibiotic bacteria, named after Alexander Yersin. We'll see a picture of him in a second. That's what they're looking for. So what this plague strain is, what this outbreak in China is the last of the 3 major waves of plague that we know about that hit humankind. So I was discussing 3 waves, they're very interesting. So the modern plague strains, including this outbreak now, they began in the 19th century, I think, in China. And they were the first ones to basically go global. So we're going to go backwards in time. So we start here in China, 19th century, and that strain spread to Australia, to the Americas, to a variety of places. And as I say, it got to Australia in the early 20th century, and there are a variety, apparently people don't know it's in Brisbane anymore, but this is a good photograph from Brisbane in 1901, with using some plague control. So it got to Australia a few times in the turn of the 20th century. Yesterday I had a really good picture on the Sydney Medical School website, congratulations Bruce, of these are rat catchers from Sydney in 1900. And there was a plague outbreak, the first plague outbreak in Australia, and they realised that the black rat was the main source of the bacteria. So they went out to kill as many rats as possible. Fantastic. That's 1900, that's 1901. So that's stress, and that's the one strain. This is when Yersin described the bacteria in the 19th century. The second pandemic, going backwards, is even more famous, and that began with the Black Death in about 1348. And we think that started in, again, mid-central China, spread along the old Silk Road, I think, into Europe, and swept through Europe. And that was a devastating, as you well know, devastating outbreak. May have killed a third, 40% of the European population, so a huge death toll. But the interesting thing is, after the Black Death, the plague didn't disappear, it just kept coming back. And in fact, there's one pandemic, they think, that lasted for almost 300 years or so. So some of the Black Death, there were cycles every 5 or 6 years of plague that went on until the 17th century. So all these medieval plagues are kind of one pandemic. And the first pandemic, and before that, happened at the time of the Roman Emperor Justinian, about 540 to 598 AD. And the contemporary writers at the time, a chap called Procopius, he suggested that this first plague started here in Africa, went up the Nile into Europe. And that was as devastating as the Black Death. Again, it may have killed 30-40% of the European population. It's one of the things that's been, this is the Byzantine era, and it's one of the things that's been attributed as being a cause of the decline, fall of the Roman Empire. That's the three plagues. So I'm interested, again, I'm interested in emergence, I'm interested in how the plague has got going. What's driven these three pandemics? So, with some colleagues at Henry Poinar in Canada, what we're trying to do is some molecular archaeology to find these old strains that have caused these early pandemics. I'm just going to show you one example, and that's the first pandemic. And I want to show you that, what we're going to get from this is that plague is a zoonosis, just like HIV, just like flu will discuss in a second. So what we've done is this molecular archaeology, which is kind of whiz-bang, fantastic modern science. And what we found here is a burial pit in Bavaria, a graveyard, that dates about 540 AD, so it's Byzantine cemetery. And there are lots of these coffins in this burial pit in Germany. And it dating to the right time of the Justinian's plague. So here are some skeletons. Sorry you can't really see, but there's a green person. We worked with colour we found, by the way. Okay? I'm just dying, just colour we don't need to see. There's a green person here, there's a blue person here. That's a third person in red. You can't really see. The light's not very good. So in fact, if you look very closely, the green and blue individuals, they're kind of holding, hugging each other. I'm not sure why, but it's combination. Anyway, so that's this. We had the cemetery here dated to 540 AD. And the really amazing thing about plague bacteria is that if you find a skeleton with teeth in, and you drill down into the dental pulp, the bacterium sequesters itself in dental pulp. So you can drill down these old teeth samples, and you can pull out, you see the pattern, you've got the plague that's 1,500 years old, and you can sequence it. So we sequence the complete genome. This number here is 7.6x coverage. That means we sample, we sequence each nucleotide, each base of DNA, about 8 times. So we've got a complete genome of plague from this Roman sample that dates to 1,500 years old. So it goes back to the genome sequence. Then you can do some evolutionary analysis, like we've shown you, and what you find is actually very interesting. So briefly, here's a tree again of plague and its relatives. The branches in black, they are all rodent strains. So plague is a rodent bacterium. It loves rodents like the black rats or marmots. The ones in colours, they're the human pandemics. So this is the blue one, this is the recent one, modern pandemic, started in the 19th century in China. This is Alexander Yersin. The one in kind of really orange colour, that's the Black Death medieval ones, okay, it's the plague doctor. And the one in green, this is the Justinians. This is the seal of the Emperor Justinian, okay. So you can see by eye, and it's very obvious, that each of these three is an independent jump from rodents to humans. So plague is like many infections. It spills over, like that chap in China, one animal infecting one human, but there's no on transmission. But 3 times at least, it's got going to cause a global pandemic. So why have these got going? Why are these 3 not? That's a question we can address. We also think, I shouldn't describe what, we also think that rather than being African origin, this is most likely an Asian. Justinian is most likely an Asian strain. So that's plague. Now we're going to turn to a current example. And as I said already, of all the ones that worry me, flu is still the one that I would lose most sleep on. I'm trying to explain why. So just to give you a view of the burden of influenza, here's some quick statistics. This is just some very simple data now showing the decline in mortality, this is death, this is mortality here, of some very well-known childhood diseases over the 20th century. Okay, this is time. So here you can see you've got things like measles, scarlet fever, diphtheria, whatever. And you can see that they've just gone down to really quite very low levels as the 20th century proceeded. That's of course due to better living conditions, better medicine, chemotherapy, vaccines, all those things have reduced the burden of childhood disease quite dramatically. Now add on to that picture 2 other diseases, that's tuberculosis and flu, which are still ongoing obviously. So this is now this, okay, and these are the new ones. So this is TB in, is that green? And this is influenza in, I guess that's kind of brown colour. Look at that. So they're still way high and still continual infections with ability disease like flu. This incredible thing here, this amazing peak in deaths, this is the 1918 flu pandemic. I'll stress that shortly. So you can see flu has been and still is a major disease burden in humans. And the numbers are hard to estimate because when people die of flu, tend in fact to die of secondary bacterial infections often, so it's hard to know exactly what the true death toll is of flu. The numbers that I've looked at for Australia, they think are around about 2,500 flu deaths per year. Again, it's hard to estimate. It's about the same number of people die of flu in Australia each year as died of Ebola today. Okay, help me get some perspective on that. Globally, again, hard to estimate, but about maybe 500,000 flu deaths per year globally. So, in the last century, there have been 4, we think, big pandemics of influenza. The first, very famously, was the one that started in 1918. That may have been the sort of Spanish flu or la gripe. I should say that's got nothing to do with Spain whatsoever. Just that the Spanish were the first people to report it. Because it's the First World War, there's a war effort, and people weren't allowed to report things, newspapers were kind of closed. The Spanish press was free, so they published that. So the Spanish was trying to tell us it didn't come from Spain. Okay. So, it's hard to estimate how many people actually died in that. And estimates vary from 20 million to 100 million. 50 is a kind of going average, but again, it's very hard to tell. In the US, it may have killed, in fact, with better estimates, about 675,000 people died in the US. A lot of them very young. Now, to put in perspective, the normal influenza mortality in the US is about 35,000. Okay, so remember that number. So 1918 is a very, very famous epidemic. So it's the first use of face masks, very, very popular. This is the epidemic curve. This is from a picture from the time showing the US and Europe, the peak. So there's a big peak at the end of 2019, Northern Hemisphere winter. It didn't get to Australia until early 1919, so a bit late in Australia. And there, again, hard to estimate, it probably killed more than 12,000 people in a decade. Well, another very cool thing about this virus, the strange about this virus, is that we have a very different mortality picture than other flu outbreaks, past and present, before and since. So normally with influenza, you have what's called a U-shaped mortality. This is age, this is death. So normally with flu, it's the very young and the very old that die of influenza, that are U-shaped. But in 1918, for reasons not quite clear, so you've got more of a W-shape. There's a peak of death in young adults. Now quite a lot of it is a source of much debate. So that's 1918. 1917, that's 1957 was the second one, it's called Asian flu, again, pretty misnomer, you're not really sure, it came from Asia. The US killed about 70,000 to twice the normal seasonal flu death toll. 1968, another one called Hong Kong flu. In the US, not really more than normal seasonal death, about 33,000. And of course, one more recently, swine flu, 2009. Very infectious, so they estimate 60 million people in the US were infected. The death toll, it turns out, was actually much lower than normal seasonal flu. Initially it looked really bad, in fact it turned out to be less virulent than normal seasonal flu. So there are 4 pandemics of humans. So that's what we had. The big question, of course, is what we're going to get next. And so the worry is that, as you're going to see, that there are strains like H7N7 I've mentioned already, strains of viruses in birds that could potentially be jumped in humans and cause a pandemic. Now, there's a number of them that we should worry about. Let's just describe one very quickly now. And that's H7N9 strain, and that first appeared in China last year, and it's still going on, so don't forget it at all. And what's interesting is some of the epidemiology is very striking. So the latest figures I have from June of this year, 350 human cases, 59 deaths. So again, this is a spillover infection. Each of these human cases is a virus that's jumped from a chicken to a human, and there's no human-human transmission. The interesting thing is this is the epidemic curve. This is 2013, this is the first wave. You can see it peaking cases. And the Chinese authorities did a really good job of trying to dampen down quickly on the epidemic. What they did critically was they closed live bird markets. The virus was jumping to humans at live bird markets. So the Chinese just very quickly stamped on that, stopped, closed those markets, and there was a big decline in the human numbers. But critically, they didn't eradicate it because it's come back again at bigger numbers this year, the second wave. And they didn't eradicate it because, and again, don't use them important, because the virus in that, as it was infecting humans, it was also spreading in the poultry virus across China. So this virus has sequestered itself right across China this is true, it's showing the spread of the virus across China in the chickens. And now it's pretty fixed in chicken populations in China. And it's still appearing in human cases. So, for example, just a couple of days ago, I found reports that in the far west of China, in the Uyghur region, you may have heard of the Uyghurs, there's a political unrest there. In the Uyghur region, there are 2 cases of H7N9 in individuals who were infected by poultry, and one of them died. So it's spread right across China. So this one I would watch. It still has the potential to turn very nasty indeed. So Australia, now we've not done too badly. We're not getting many exotic strains, flu strains into our country we need to be concerned about. But they do happen on a fairly regular basis. Luckily, nothing bad has come in. This map here is just showing you some of the strange flu strains that have come into Australia in recent years. So here we have some swine flu here in Queensland, swine flu here in Western Australia, avian flu outbreak in the Sydney region, it's 10N7 strain, and the ones in green, blue, that's the most important ones. These are H7N strains, but low virulent strains. So avian flu comes in 2 forms. Very nasty, highly virulent ones, and less nasty, low virulent ones. And luckily in Australia to date, all the avian ones we've had are of the low virulence type. So we've not had a high virulent flu strain coming in. The question is just quarantine going to handle it? So the good thing is we are doing lots of surveillance, we are watching this. So the question is, what's the likelihood of it coming in? It's very hard to say. One possible route of these viruses to get into Australia is not through poultry. Poultry are the vehicle for avian flu to get to human. But avian flu, actually, its major reservoir species are not poultry, they're other types of wild birds. And these wild birds can migrate, they fly, obviously. I'll discuss this in one second. And so birds, rather like airlines, have flight paths, okay, called flyways. And this map of the world, these got lines, these squiggles. These are major flyways that different birds use. You can see it's dotted line here. This is a flyway that some birds do to migrate from the Arctic to Australia. Okay, so that's kind of avian, that's an avian flyway. Now, the wild reservoir for avian flu, again, they're not poultry, they're other species of wild birds. And there's 2 major groups. One are the anceriforms, so ducks, swans, geese, and those sorts of things. And we have lots of those in Australia, but they're non-migratory. Okay? So they're not going to go up there and get a virus and come back with it for us. But if a virus did get to Australia, these ducks and things, they could be a reservoir here. Okay? The more worrying sorts are these lots, Shadiriforms, I can say that. So things like waves and shorebirds. So they do migrate from Australia up into the Arctic. So it's beyond all possibility, they can pick up an exotic avian flu strain and migrate back. So that's the reason to watch, and there is surveillance going on. So I'll give one more quick case before I finish up, and that's, so I think flu is the one that I'm most worried about, because it can be very, very virulent, like COVID-19, and it's very, very infectious. So that's kind of the worst case combination. One other thing very briefly that I mentioned are hemorrhagic fevers. So Ebola hemorrhagic fever that are really, really nasty. There are lots of other hemorrhagic fevers around we may want to think about. So one of them are, so I would look a lot in China now, the Chinese CDC, and in China there are lots of hemorrhagic fevers floating in that population. So for example, this is a city called Longquan in Zhejiang here, and this is the outbreak, this is the incidence of particular hemorrhagic fever called HFRS, hemorrhagic renal syndrome, caused by a hantavirus. We can see every year there are 50 to 100 cases of this hantavirus infection, hemorrhagic fever like this in China. And the death rate is pretty high. The death rate of this is about 10%. This is a very nasty thing. But lots of them don't know what the cause is. So what we've been doing is looking at this kind of fault line, again, to try and find out what viruses are out there in China that are causing these hemorrhagic fevers. And what you do, and we're looking particularly hantavirus, we're interested in, what you do is you go to places in that environmental scale before you go to the wild, go to fields, caves, around houses, everywhere, trapping animals and searching for viruses. Particularly, a very good thing to do is to put rat cages and rodent traps out to see what rodents you can catch. And you can catch, it's very, very easy to pick up, this is a rat here, very easy to pick up rats living around these houses in some of these parts of China. And you can isolate viruses and analyse them. And again, it's a bit technical, but we've done that, and what you find is very interesting. This is true of hantaviruses, and details are important. Imagine you have a blue hantavirus and a red hantavirus. The ones in ordinary font, they are rat strains and rat hantaviruses. The ones in kind of bold italic font, they are human cases. You can see the human cases are near identical to the rodent ones because they are spillovers. So every one of those cases of hantavirus infection, all those deaths in non-quam, that hemorrhagic fever, what they are, each one is a spillover event from a rodent to a human. There's no human transmission yet. It's stage 1 of movies, but who knows what could happen. It's quite an interesting situation. Now, if you look at the evolutionary history of hantavirus, I apologize, not really slide, look at their long history. What I've drawn here is a tree of the mammals, the host, and a tree of the viruses. If there was no species jumping, no cross transmission, those two trees would match each other. You can see some horizontal diagonal lines, that's species jumping. So here, these haven't got going in humans, but in the past, some of them have, so watch this space. So that's China, so you think, oh, so what? But in other cases too, these hantaviruses, rodent-borne diseases, are jumping into humans, causing spillover infections and sometimes mortality. Here's a picture from this is in Colorado, in the US. This is a related hantavirus syndrome called hantavirus pulmonary syndrome. And here in Colorado, in recent years, every year there are 5 or so cases of this hantavirus infection in humans, and the ones in there are people who die. So they're jumping, they're infecting people, they're causing death. Luckily, as yet, there's no human transmission. Here, this is Saskatchewan, Canada, the same thing. This is just a few months ago. 2 cases so far of hantavirus jumping from a mouse, a deer mouse, into human, causing death. So again, hantaviruses, as yet they haven't got going, but again, they're kind of a thought line more than watch. So, given all that, last part now, what can we do? What kind of state are we at? So, how to deal with pandemic disease? It's not what I'm saying now, it's kind of obvious, not complicated stuff, what we actually need to do. So very briefly, we need to build capacity at both national and international scales, obviously. We need a very strong international health network with data sharing. That's got a lot better, I'll discuss it in 1 second. Obviously, a closer working relationship between clinicians and scientists and veterinarians, because these diseases I was showing you, human diseases are actually animal diseases that jump species boundaries. We need a multidisciplinary approach involving ecology, microbiology, veterinary medicine, human medicine, lots of different things built together. And really good ongoing surveillance at these fault lines from humans to wildlife to hospitals, because that's where the jumping is taking place. So we do a lot of this already in humans right now. If I had to grade us as a planet, I would say we're about a B to a B+. Okay, we're okay, but we definitely could do better. And I think the current Ebola outbreak has really put that into focus. So we've done, we are there, WHO is there, we are trying to stand things down, but we're a bit too late. I think we should have had a more military-style surge of medicine at least a month ago. So we do need to act quicker, more collaboratively, bigger in these sort of outbreaks, and try and bring them down. And I work here at the American Institute, and kind of what we want to try and do is some of this kind of local scale. So hopefully we're going to do a little bit to kind of make the world look better in this kind of space. Again, not too bad, but I think we could definitely get better. So one thing where I think we are doing really well, we don't need to have any improvement almost, is in the identification and analysis of pathogens. We are now really good at this. So to put it in perspective, in the early 1980s, when AIDS was first described, it took 2 years to find a virus that caused AIDS. 2 years to HIV was discovered. Now I think we could reasonably expect to find the cause of a novel pandemic in 24 hours. Okay, so the technology for doing that has moved on leaps and bounds in the last 30 years. The details are not important how that's done. There's a chap called Ian at Columbia, who's a kind of global expert in this. This is his kind of pipeline from sample to analysis. And he has a fantastic protocol for doing it. So this again, in theory, we can incredibly quickly work out what the agent is that's causing a new disease. Once we have that, we can also do in real time analysis. We can do evolution analysis, I've shown you something I do. We can do evolutionary modelling to work out where it might spread and how you to control it. This is some maps in the UK from outbreak 2001 showing some modelling. And also we can do real-time public information service. So there's lots now wikis that you can log on to, and you can watch the spread like Ebola, like SARS, like flu, in real time. So we are really good at it. So I don't think it's this part that's the problem. It's the world unification to act together to stamp on diseases that's the really improvement. So Australia, again, I think I'd grade us a B to a B+. I think we're pretty good at it in some respects. We obviously have a very strong medical infrastructure, lots of very smart people. So I don't think we're in a bad space. However, I do think we could do better. And I think the global problem, I think, is exactly the same thing that's in focus here, that we need a national overarching body that's going to take care of infectious disease control. So I think Australia's CDC would be a very good thing. It's going to link the states and territories, and it's going to link infections in human animals. So I, as many other people have suggested, would think it's a very, very good thing to invest in. So this is not, again, really not my idea, it's an old idea. Just to give you an example. Last year, the government had a report on a project report called Disease Have No Borders, and they're correct. And part of that report was a discussion of the need for Australian CDC. And they had a variety of opinions, but in general they thought that was a good idea. So I'm just going to use some of their words because they're more elegant than mine. So here's some quotes in the report, which you can download and read. This is actually quite good. And they say the committee is concerned that the lack of uniformity, infectious disease control, and adequate coordination between corporate agencies across all levels of government could potentially compromise Australia's preparedness to respond to a nationwide outbreak of infectious disease in the future. Australia's resources and coordination and national expertise may be stretched beyond capacity should Australia experience an outbreak or pandemic more significant than we've had in the past. So the point being here, we've got a way of being isolated. That isn't going to work in the long term. We need to kind of do better than that. And the final quote, this is one particular committee member, and this is kind of exactly what I would say, so he said it very well. Australia has a very strong capacity in lots of areas, but there tends to be fragmentation, it's very true, at both national level and our capacity to respond regionally and more broadly, because we lack the sort of coordination of achiever. And that was sums up what I feel being here for a couple of years now. That it's great stuff here, but the linkage, that framework, is not really there. There's too much fragmentation. So I would also add my vote to Australian CDC. So all about 2 slides ago, so this is give an example of what can be done. This is China. So China received an awful lot of criticism post-SARS for being too slow, not giving out data, just being too close. And so following SARS, they built a nationwide network of CDCs, and that's been extremely successful. So I work a lot with the China CDC, and I've been on their kind of field trips. So you can go to very remote villages here in China here. This is local cooking facilities, so it's really quite amazing stuff. Local fauna, okay, so lots of good flu vectors lying around. This is the local CDC office here in this little town in China. This is the health instructions. So I was there during the first week of the H7N9 outbreak in April 2013. This is the director of this village's local CDC. It's a real amazing network. And on this board here is written instructions for H7N9 for villages to read. I'm sure that I hope it's what it says. And it's, I don't really Cantonese, it's from the Mandarin. It's saying, I think, the virus comes from chickens, don't go to the markets and be careful. So that's the local scale. The national scale, China has done, I think it's a stage, but China has done a very good job at clamping down on H7N9 and sharing the data. So I think they're really a model for us for the future. So to conclude, so what I hope I've shown you is that animal species carry an enormous number of potential pathogens that could jump, in most work, that could jump genes in the future. The way we live today is just going to make that more likely. So there's changing land use, there's deforestation, we live in huge cities, we travel between their cities, more refugees. It's one reason why this part of Africa has got the big Ebola outbreak, is that there are a lot of refugees that displaced people. Because Sierra Leone had a really horrendous war for about a decade. So it's no surprise that infrastructure is very weak there. It's allowed Ebola to take off. So I think that, as I said at the start, that new pandemics are inevitable, but they're not necessarily destructive. I would still pose that the ones we know about, flu is the one I'm still worried about most, because it can be both virulent and very infectious. And we need, as I mentioned, ongoing surveillance with national kind of networks to really kind of make us respond better to those in the future. So finally, so lots of people involved in this work, I haven't got time to describe them. Some further reading for you, some homework. If you're interested in how viruses jump from animals to humans, I would strongly recommend David Quammen's book called Spillover. It's a fantastic, I'm in it. Apart from that, it's actually quite good. So it's a very good book. And Peter Durton, one of our great scientists, this year wrote a fantastic book called Pandemics, What You Need to Know. A kind of keep calm, carry on guide to pandemics. And I really would recommend you buy a copy of that and keep it next to you in the person cabinet. It's very useful. I'll stop there. Thank you.